Hello everybody, John and I are back.
Aloha.
So we just wrapped up a brief update with Kīlauea. We talked a little bit about the ocean entry and Fishery 8, and we talked a little bit about the hurricane as well. So I want to kind of just reconnect with you guys and talk a little more of the science that we're seeing. So we will get to that and give you guys a chance to join in here. And yeah, we're going to talk a little bit more about the science of what's happening, you know, some of the ideas that we have. We did some sketches to kind of try to help you guys understand what might be going on here, so we'll see if that helps at all. And good to see you guys. So maybe the first thing I can start off with, and we can come back to this a little later on, is the tilt, as we often do. So let me get that lined up over here for us on a handy iPad. So okay. Here is our tilt plot from today, and you guys may now notice that the summit tilt signal is completely blank. We're not getting data from there anymore right now coming to the web. So the USGS assures us that they're still collecting the data and they're seeing nothing significant in it, and that's what we got to go on. And we have a station from Pu'o'o still that basically is still showing us within a very small scale on the side some slight deflation. So that's, you know, basically a good sign as far as anything making it down through the rift zone towards Fishery 8 and bubbling out. So we basically have no pressure increasing coming from the rift zone, at least within Fishery 8. The pressure is, as we were describing with Kīlauea, from the gas collecting and bubbling out, that, you know, the gas can create quite a lot of pressure in localized areas. So that's the kind of zoomed in version. Let's kind of look at our week-long version here, so we can kind of see in the grand scheme of things that the Pu'o'o line, the green line, is still basically mostly flat. A little kind of wiggle right in there, a little wiggle right in there, but, you know, all within that, let's say, a half microradian, more or less. Well, maybe almost a full microradian deflation from over the course of a week at Pu'o'o. And yeah, looking at the whole month, we can try to zoom in real close, and you can see that really these are all just little variations in what's basically still our flatline signal on the grand scheme of things. So that is our tilt. Maybe we'll just kind of look through it, or you don't see any funny signal here at the summit GPS vertical at South Caldera. We talked about the one earlier in the week here at Byron's Ledge, but nothing recently here as well. And we can see we've actually lost the signal for Kīlauea North as well. We still have our GPS coming in. It's still showing that kind of stabilization here at the bottom ever since the collapse has stopped. And that's really all we have to see there. That's really different and worth addressing right in that particular point. John, anything to add about this in particular, or?
Not too much in particular. Like we've mentioned before, the strongest signal that we have at the moment is flat line, and it's still flatlining. And so remember, the longer that flatline situation continues, the more and more likely it is that it's POW, not going to resume. So overall, we're watching all these other details, but the flat line is the only thing that is significant at the moment. So
right. So yeah, well said. Let's maybe look at some other signals that we have here. Well, I got the signals up on an iPad. So let's look at the earthquake page, and loading up the earthquake page. You still only see one earthquake in the last 24 hours that's registering on a map. It's showing as a 2.6. So all the earthquakes smaller than that don't really show up on there. And the reason I mention that is we can switch over to our where is it? Over here. Over here. This is the seismograph for our Kīlauea area, which is uprift of Leilani and downrift of Pu'o'o. And what you might see is we see lots of little signals that actually might be little microquakes, small magnitudes that wouldn't show up on the map. So we are still having some little action down there. It could be a little rocks being broken with small earthquakes. There could be some little gas bursts. Sometimes when we see a signal that doesn't look quite the right, like that's clearly an earthquake shape signal right there, but sometimes you see ones that might be more gas bursts kind of thing. It's hard to say exactly. And beyond that, we have kind of the background weight of the ink, right? So you guys can clearly see now that I've scrolled down a little bit how we have a much thicker background tremor, right? The vibration is making the background of the line is much thicker down here in the last, let's call it 8 hours than we did before that. So often this signal is associated with gas moving through the system and that kind of degassing. So the gas kind of moving through that conduit and vibrating the walls of it are what's causing that tremor to actually happen. Yeah, we are. So, that actually corresponds to what you might see as far as gas pistoning. You know, that might not be surprising to see like during times like this. It might be when we see the spatter, and we might have times of recharging essentially before it kind of resumes that cycle. So if we look at the image right here, I believe that the image we have from just this morning was at 8 a.m. So 8 a.m. on here kind of corresponds kind of right in this zone right in here. So we can kind of see that it doesn't look like it's quite as active right there, but maybe we saw the signs of the gas coming out maybe through here. It was spattering more and more and more throughout the day possibly. So maybe we'll see when we get any images if that's true, if anyone has a chance to capture that. It's harder to capture that when you fly over. Yeah. And you get like a snapshot here and a snapshot there to really see how it's shooting into the air or changing from 15 minutes to the next 15 minutes, which is sometimes what you need to see in that kind of time scale. So while we're looking at seismographs, I'm going to show you guys the Summit one as well. So let me just make sure this is a fresh. It was not fresh. So here at the Summit, you guys can see similar kind of gas release, possible tremors through here, right? You can kind of see the bands kind of increase, then kind of decrease and increase, and that's the simplest explanation. You know, of course, we don't have any more data to go on and just telling you guys what the patterns generally mean without knowing exactly what's happening up there. So, but that's just to show you guys, you know, how much the ground is still moving locally, right? So people, you know, talked about in the early days of Leilani, oh, we heard the ground moving and trembling all the time, but it didn't come up on the maps, and you know, that kind of thing is still happening around, not so much in, I mean, possibly in Leilani, I haven't heard that as much, but you know, we do see that on another plot that there is still a lot of kind of movement happening in the ground. So this is expected as we kind of either wind things down or adjust and pressure downwards, whatever happens after that. You know, it's an expected thing and nothing to freak out about here either. Look at some of the other signals. Here we have our tilt from Pu'o'o for the whole last month. So back in here, we still had our collapse events, these sharp lines, and you guys can see both lines, which are basically different components, whether it's north or east, both trailing off, going downhill, and basically a deflation pattern still. And looking at our scale actually matters in this point. So the bottoms of the line are down here at -5, and the top of the line at the beginning is kind of +5. So we're looking at about 10 microradians over the course of the last month or so, which is significant at that point, size of deflation. You could say that maybe it was a little steeper and maybe it's flattened out a little more, so we have to kind of keep an eye on that and see what's happening there. But that's what we have for now. And likewise, looking at the Kīlauea, Opuna tilt, you can't really see a whole lot because of our scale of the collapse events. We're kind of spiking up here above 40 with these big spikes. But if we zoom way in over here, you can kind of see, looking at the pixels of those lines, right? There's a slightly up, kind of flat, slightly up, slightly down, and then down, and we're kind of stayed 1 pixel down. So you might say arguably slight deflation. So there is that going on as well. Basically, it's just all reinforcing the signals that the volcano is, every way we look at it, is not showing signs of inflation, not showing signs of movement or connection. These are the instruments that we have that are still online. Of course, we're missing the Summit one, which is hugely important, but we just got to go without it for now. Yeah. And let me see what else we got over here. Anything to add to that, John, while I look over here?
Here I am. Just again, like the reason we're covering these different data plots from each location is because, once again, we want to have multiple lines of evidence that are telling us something. And right now we're not seeing any coordination or indication in these multiple lines of evidence other than it's generally flatlined and there's still some tremor and things happening within the volcano, but that's to be expected until we see gases and spatter in the vents and inflation and increase in our larger locatable earthquakes. Then there's no reason to suspect that pressure is building anywhere. So we're scanning each layer of the data to see if they're indicating one thing. So that's why we go over these different things every time, just so you know.
Yeah, thanks. Awesome, John. Yeah. So while we're doing that, let's try to do a little more comprehensive, make sure we cover our bases today. Here is a webcam in Puna traffic, looking at the temperature of the plates that are still showing an average of 108, today. So that's still within our range and doesn't seem like anything unusual is happening there. So that is all good too. I wanted to, let's see if I still have this on here. Oh, yeah, I'll show you guys this capture from the webcam earlier. It just happens to be a pretty sight here, a view from about an hour and a half ago from the summit. You guys can see the nice rainbow over there. That's kind of dipping into the deepest part of that collapse of Hale Mau Mau down in there once again. So just a nice image to share with you guys. You know, slightly different view of it, looking a little further to the south, but that was a nice one up here. So that's showing you guys we're still trying to keep an eye on everything going on there. That's all the signals we actually have. I can show you guys a couple of the pictures in case any of you guys did not come in with the Kaika update earlier. So I'll show you guys some of these pictures. This one is the one that is maybe the most significant one to us today, is the fact that we have two glowing holes in here, and actually all the light colored gray material is fresh lava that's been spattered out and has been shot out by little gas and little clumps and just landed around here. So not a whole lot of gas. It's not shooting in the air nearly as high as it was before. It's just high enough to land it right there, right? As opposed to before, it made this entire giant structure, this giant hill. So it's really a much smaller scale than any of that. But it is actually throwing lava out, you know, so that shows that lava is still right beneath that surface, and gas is pushing it up and throwing it out still. This is nothing to be very alarmed about as far as eruption picking back up. It is in fact a sign of it's not slowing down very fast though. So, you know, the slowdown takes a while. The kind of, if it is dying off, it's not dead yet. It's still hanging on and showing signs of life, and gas moving the lava from those shallow dips out into the surface once again. But at this kind of stage of the eruption, it's all about the gas coming out, right? So we've seen that across the plates, and we've seen that in the cracks in 130, and you know, in Leilani, we've had reports of extra gas coming out of there as well. So more gas coming out now doesn't mean anything. That kind of gas will kind of keep bubbling out for a while, but the fact that lava is still there at the surface being thrown out, that's the more important part of it, not the gas so much as the lava being shallow.
Yeah. On the one hand, I don't think they can hear me that way.
All right. I don't know what it is with my phone, but here, let's turn it around.
On the one hand, if it was just a glowing puka with gas coming out, it could be expected. It could glow a long time, even if lava is retreating far away. We've been discussing that. But there's lava being thrown out with the gas, which means the lava hasn't gone that far below. And so maybe this is a good segue into some of our geophysical analysis of what might be happening inside the volcano.
Sure, let me show the last three pictures. There's only three more pictures, right?
Pictures.
So, and then
sorry, pictures first.
After these three pictures, we'll switch to our very nice cartoons that John drew for us earlier today.
You help.
So, okay.
These cartoons had Philip's approval.
All right, so let's show you guys. These images are from Anthony Quintanao. Thank you, Anthony. His post is on Hawaii Tracker. I will have to tag you later on when I wrap this up here. But he's got a series of 3 images. This is a picture of Fissure 8 from this morning. And you kind of can see that area that we're talking about, the spattering, is this little gray patch right in there, that little zone right in there. And this whole area right here, it's hard to tell. It's actually all sunken in. This is probably, oh, I don't know, several tens of feet lower than right here. You kind of can't really tell from this angle quite as easily.
But can I add one thing here?
Add everything you want.
Okay. So the spatter that has been photographed today was coming from this area here in the gray there. Last Thursday, when I did an update with Philip, the glowing puddle of lava was in the pit up over here, and now it's glowing over there.
You want me to?
Huh? Yeah, Ken. Whoa, yeah, that shows it. So there's the glowing puddle. Looks like it might have been actually some thin crust over a little bit of like lava ooze right there. It's a little hard to judge.
Here, let me zoom in for you.
Yeah, so in this image, it starts to look more and more to me like that is a surface of fresh lava that was squeezed up and maybe oozing out the edges of the cracks a little bit. And then apparently it retreated or sealed itself off. The new glowing pukas are over in this vicinity here. And so we've got different configuration for at least what part of it is degassing and glowing today versus a few days ago.
On the surface, right?
On the surface.
At shallow depth, those are all connected, but obviously, if the surface changed, it changed for some reason. whether it's gas either breaking a new little hole and through some crust, or whether it's lava being squeezed up and, you know, covering what is essentially a hollow hole that you can't see below that crust. We still believe there's those two spots of weakness in there. So here, let's get a couple closer views here from Anthony's photograph. So this upper one right here is the one John just pointed out, I believe, right? Let's zoom in a little more.
Yeah, right down in there.
So there it is, right? We just see like a little hole with not a whole lot of even fume coming out of there. And then down over here is the one that's putting out all the gas. And he's got one more photograph that he managed to catch through the fume. And so here, let me kind of give you guys a full view. Is looking straight down. There is that upper, let's call it the more southern, southwestern spot. And over here, the other spot, right? And if I zoom way in on this, this doesn't show up as well on a camera, but right in there, that's a little spot of orange red right in the middle right there. So you guys can check out those photographs on Hawaii Tracker.
Yeah, we should reference too, you know, that glowing spot is maybe only a foot or two wide, a couple feet wide at most. It's very small, so
yeah,
it's on that order.
So yeah, those are the photographs we got, and now we'll turn to the little cartoon we have. Maybe I'll come around to your side, John. Yeah.
Better light. Yeah.
Get better light. So let me change positions here. We're down here at the hub. Here, put it right on the bench.
Yeah. Okay.
All right. So
I don't know how we'll do with the shadows, but
all right. Let's see.
Working on there.
I hope so. Hopefully they can actually hear.
Okay.
But so here's John, and here is our cartoon. So just to kind of reference you guys. Oh, here, let me bring up the other one first. So, sorry guys, let me show you guys one last thing, which is that we actually started off this image looking at a published image that came out by Michael Pulland in the U.S. Chess Professional Paper 1801, which has been a pretty good reference for us.
We're not just making this up.
Right. So here's our base image. Right. So there's this image is online, and you know, this is the most recent published, most complete kind of cutaway view of the volcano. So you guys can kind of see more or less. We have our, let me get my pointer here, our main vertical conduit coming up. This is our deep magma chamber, labeled SC for South Caldera. Our shallow chamber, labeled H for Halemaumau. Our southwest rift zone, which is down here where we see the seismicity coming through, and where we see eruptions coming up farther up here. So let's ignore that complication. Ignore this complication of the upper and lower over here in the east rift zone also, but here's an east rift zone connected in this diagram, you know, from the South Caldera. And it's from there we kind of have eruptions being fed to the surface from various places, for example, Pu'o'o, or farther off the map from Leilani here. We're going to zoom in and focus on this area right in here. We have this area labeled K is for Kīlauea underneath that South Caldera area, as well as another storage area. And this little zone right in here, this little, it's almost like a little uvula, right? That's kind of in between. And this
That's the thing that hangs down in the back of your throat.
Oh yeah, exactly. Yeah, that thing that looks like that thing that hangs down in the back of your throat. So it's hard to say exactly because this thing is like just one slice through the volcano, right? It could have been if you slice it a different way, you wouldn't see quite that shape. But that's the area that's really the big question mark for us. And so we've taken this whole schematic and we've redrawn it for you guys in our own whiteboard version, so we can start analyzing this a little bit more.
And we can draw on it and we can erase things. So I'll talk twice as loud as normal since we sometimes have issues with the sound on this side. So we've cut through our volcano so we can see the pipes basically. And so we've got the caldera up here with the original Halemaumau crater is directly above one of the main conduits that comes to the surface there. And below that we have the Halemaumau reservoir, which we've often been calling the shallow summit reservoir. And below that, that south caldera is even bigger. And this weird little thumb of it, which is under Kīlauea reservoir. And see, through this system, lava is probably coming up from very, very deep, and probably most of it moves all the way up to the top of the system before it gets fed back down into one way or another. And the most active route is out the east rift. And so to understand, you know, we have a giant wide volcano, and this pipe is not exactly like a pipe. That's not exactly how it forms. But this is still, you know, a couple kilometers underground. So the lava, when it's moving out through the East Rift, most of its journey is like below sea level, all the way down out here to Kapoho. It's deep inside the mountain, and when it does break the surface, it's forming cracks and breaches the surface through the fissures. So here we have Pu'uo'o, and it was feeding off of this well-established East Rift conduit for many, many years. And you can also see that within the rift zone area, there might be these old pockets of magma that might have begun as an eruption like Pu'uo'o and just stayed in there. And as far as we know, the plumbing system was open all the way at least to Pu'uo'o. And in the past has fed eruptions down the same path all the way out to Kapoho and beyond. So it continues all the way underwater down the Eastern Rift submarine part of the volcano. And so, again, the significant area that we're concerned about is how is this all connected between the Summit Reservoir and the East Rift and Pu'uo'o. And so we've kind of analyzed a couple ideas about it down here. Should we go from there to here?
Sure.
Is that?
Yep,
I don't
absolutely.
know, the best way to explain it. Maybe.
Right. So here, just
we're trying to use these drawings interactively, so we can draw on it and we can change it if we need to discuss something.
I've got a couple of things real quick. One is something that John mentioned earlier, which is not obvious in this section, which is this is really a blade. We're looking kind of at the edge of the blade, right? So if we were to turn this, we'd see it's actually skinny, but you can't see. It might look like just like a tube, but it's actually a blade, and probably actually a series of blades side by side. So kind of just help you guys imagine that. And then we're going to look at these. We're basically redrawing what we have up here, down here 3 times, right? And so this is earlier time, recent time, and speculation for what's happening now or in the future. So let's go on one at a time now, John.
Yeah, so from 1983 to the present, we just picked those numbers because that's while Pu'uo'o was active. And maybe it changed a little bit during the period that Pu'uo'o was active. But during that time, we know we had some kind of open system, or I don't mean in the less way, but we had open transit of lava through the magma chambers and out to the East Rift, and it was getting at least as far as Pu'uo'o and coming to the surface at Pu'uo'o real consistently. And so we've inferred there was some kind of a blockage or constriction, or for some reason,
or an easier path up.
And it just didn't have the pressure to push it down into this next section. But that's what we're drawing here, is for whatever reason the lava was going to the surface rather than continuing on route down the Eastern Rift. So something to go ahead.
So these kind of block, we kind of drew this thing as like a one continuous with like one little block. It just might be like a segment with all different points where it might possibly catch. And we have a question mark over here. We're not sure if that might have been something over there. Is there like some kind of boundary right there? Is it the edge of one of these segments? And we kind of made it simple for you guys, and let's just show the one relevant to that eruption of Pu'uo'o.
Right. So for some reason it wasn't going past Pu'uo'o into the rest of the system at that time. But after May 3rd and August 2018 to where we are now, obviously the system changed a lot, and the lava was able to overcome the pressure it needed, or whatever was the exact situation, and it overcame the blockage or constriction at the Pu'uo'o area, and it sent lava continuing on down the rift all the way to Leilani at least.
So we bypassed right from here.
Bypass.
No longer coming up, just bypass.
No longer coming up, drain back down into this system, and is going back this way. And it kept driving, so we had the earthquakes as the lava pushed down under Leilani, earthquake after earthquake, and the earthquakes didn't get much further than Fissure 17, or the Pu'ukapoho, the green crater. That area probably represents another one of these constrictions or some kind of pressure gradient that the lava couldn't overcome to continue on down through the rift system.
It was easier.
It was easier for it to come up through Leilani, which we have labeled F8, but that really stands for our entire set of fissures. So our mountain is enormous, and so where we see this one, that's our last fractures of rock that led to our entire fissure system, not just Fissure 8. So on the scale of the mountain, it's all a small area here. And then next to it here, we've been debating about the possibility of a magma body was near the rift or within the rift to just about where it got to. And this might be the magma supply for Fissure 17, which erupted on its own. Old lava came to the surface, and that is kind of representing about as far as our lava was able to intrude during this time.
Right, so that's why we see different lavas, because that's disconnected right there.
Right, disconnected, yeah. So the Fissure 17 produced lava that was not related to the lavas we kept seeing out of our other fissures. So we've heard about the 1955 lavas were squeezed out of those fissures in the early stages of the eruption, and then later we got the hotter, more fluid lava that came out of Fissure 20, 22, and Fissure 8. But 17 had a totally different chemistry. So somehow some other pocket of lava was disturbed by our intrusion and came to the surface at that time. And we're only putting it on here to think about it as that is kind of marking as far as this intrusion of lava progressed under Leilani into Lower Puna.
Because it didn't connect.
Right.
Yeah.
And you see what's happening up here in the other part of our drawing. The crater has been collapsing already by this time. And it had collapsed initially, at least it was collapsing down the main conduit above the reservoir. But now something's obviously changed. So if we jump to now, or thinking about what's next, something has changed. We're no longer seeing lava come out of Fissure 8. We're no longer seeing any inflation or any changes at the summit or at Pu'uo'o. So we've drawn in our question marks. One question we have is if the collapsing at the crater has actually collapsed down enough to start compressing and changing the plumbing of the shallow summit system. And if so, did it collapse far enough to disrupt these connections through that Keanekakoi thumb over here and into the Eastern Rift? So we've got these heavy questions of, is there some kind of disconnect now between the East Rift and the summit storage? Is the collapse great enough to disturb the connection of the shallow storage with the deep storage and the East Rift, etc.? And so there's a lot of space down there. So if we can look at this larger drawing again. So we've got our first little pipe that led up to the old Halima'uma'u crater. The crater collapsed that pipe first, and it kept collapsing to at least about this level. And that means, you know, our crater, we could draw it on here as the bottom of the crater is, what, about a half a kilometer, a little more than half a kilometer?
Right.
Below the original surface. So if we drew that on, that means the actual pit reaches down quite far. And we have our new collapse crater is much, much larger within the old crater, right? And so that's the part that's actually physically void, collapsed. But in here, that might also mean we have all this crumple zone where the material crumpled down below it. All of this material collapsed downwards into the magma chamber. And this is where our questions lie. How did it affect all of this interconnection down here? Has it actually collapsed the whole shallow chamber?
Yeah, exactly. This part right here he just drew, and this is empty space. And this part down here is rubble. Right? So you can see that that's how far down do we draw that line. He happened to draw it right through the bottom of this H. Did it go farther down? That's what we really don't know. Is
further down?
Did it collapse down all the way to here possibly? You know, like what? That's what we really don't know.
And remember, we're not making this up, and it does have a scale to it. So remember our scale. These are kilometers down, and so this is the scale of our drawing is provided by USGS scientists who've researched a lot of different lines of data. So we know these are the approximate depths for where these interconnections are happening. And so when we looked at the data earlier today and just started brainstorming about it, it's plausible that all this material has collapsed a lot of the features that used to interconnect lava and allow lava to transit up there.
Yeah, so we can pretty much like erase all this. This is all gone.
That's all gone. That's all empty space now.
All this structure in here is likely gone too. Let's erase all of that. Right, so then what are we left with down here?
Down there.
And that's the question, right? So. And, you know, did any of those chunks that were here, did those chunks actually just stop and is the bottom here? Do we have some chunks going farther in? Is it possible some chunk could have gone all the way down in here? Who knows?
Right. And we've been thinking about that because, you know, in this drawing, we all tend to imagine it as these pipes are all just full of liquid lava flowing around, and it's not that simple. There's going to be solid rock inside of these chambers, slushy rock, plasticky rock, silly putty textured rock, and there's probably all sorts of subtle structures inside that we didn't know about, and there's probably solid pieces that can continue to fall through the system and gum up the gears somehow, if that analogy works for right now.
Yeah, awesome. So that's the little summary. It's basically the same thing that we've been talking about, but we wanted to show you guys a little more visually, right? So the question came up: where is the water level? So
I knew. I just grabbed my blue thing.
I saw you grab that.
I just grabbed the blue pin before they asked that. So on this scale, the amazing thing about how big these volcanoes is, we always talk about how deep the water table is when we're giving tours and stuff up in volcano, but on our scale here, it's like way up here. The water table is somewhere, does this look right to you, Phil?
Yeah, drop parallel to the surface.
Yep, parallel to the surface, like that.
Yeah, and you can go take it all the way to the sea level at the right end of the graph if you want.
Yep, so it stays like this. And in some areas it's probably a little closer to the surface, but it leaks out the edges of the island at sea level. So that's where our water table would be. And so it's quite deep, especially if you're at the summit of the mountain. It's closer to the surface if you're very near sea level. That's just the way it works. It's called a freshwater lens. But see, what we do know is that our crater has collapsed to at least the level where it should allow groundwater to begin intruding, unless there's lava there to drive it away.
Yeah, so this is where the potential of the lake eventually exists. Is if that stays cold and stays rubbly and water moves in over years, then that's where it would be. And yeah, that kind of, put in context, we talked about the chants that Don Swanson is researched and combined with a Hawaiian kapuna that refer to 4 different ponds of water at the bottom of the caldera after the 1500 collapse. So we know that at least this scale, whether we believe that when it collapsed, the actual size of the hole wasn't just here, it actually came all the way to the side over here, so it was bigger, right, coming all the way to this side, but it was definitely at least the same depth because we had that same intersection of water table as we have right now. And that's why we, when we talk about the potential for explosions existing, volcano long term, that's why they exist. The longer it goes up to the summit with nothing changing and then water moving in and magma coming in afterwards, then you have a chance for explosion after that, right? So, but it takes time for that to happen, so we don't think that's imminent right now, but that's kind of how it works, just to kind of
And that's a
keep
weird
that
thing. I think it's counterintuitive for a lot of people's understanding. Normally, the water can't get into the magma. The magma's too hot. It drives the water table out of the way when there's lava in it. Now that the lava is gone and the rock begins to cool down, that will allow the water back in. And that's not a problem on its own until the lava returns, because the lava can always intrude into the water, not the other way around. So the question is, if the crater up there is quiet enough for long enough, and then lava quietly starts to re-intrude below that water reservoir that starts to form, then it could lead to steam explosions. The other theory is if soon the lava returns to the summit rather than coming out in Leilani again, then it might drive away any of the groundwater, and we could have lava eruptions in the crater without steam explosions.
Yeah.
So there's time frames to consider, and there's also the amount of lava to consider. If it's a small amount of lava, it'll have a greater chance of exploding because there'll be more groundwater interaction.
Yeah, so okay, so just getting a brief comment for you guys who are not metric. A kilometer is about a half mile, roughly speaking.
Yeah,
a little bit less than half a mile. You get your blue marker. I'm going to make a slight little change here. So what we got going on now is our water is actually not in here.
Yeah, it's not in there yet. I was drawing if it got in there.
Then let's give it a little space on the sides.
Yeah, there we go.
Right, and then we can maybe draw a dash line. Something like this.
Yep, that's better.
And then maybe you might have some like steam coming up at the edges of the surface. Somewhere in there you would be expecting to see at some point a steam coming out around the edges of that crack, kind of like that.
Right. but the water has not, as of yet, maybe it's beginning to, but it hasn't intruded into this collapse basin yet.
Yeah. So yeah, it's too hot. It's too hot in there. So there you have it. So that's where that chance of explosion happens. You know, and as John says, it's really magma coming into water. I believe more so than the other way around. Although the one possible exception is a big earthquake, and then kind of put them side by side. You know, that's one way water can quickly get into where the magma is. If a big earthquake opens a crack and the water is on that crack and flows into that crack, then you could have that kind of thing happening as well. So that's kind of always been a possibility in a volcano. Like, you know, as long as all of us have been here, even if we didn't know it, that one big earthquake could put water near the magma and cause an explosion. You know, so that's no different than, you know, the background level risk that's normally there. But it has always been a risk, and still continues to be a risk. But of course, you know, we would expect to see something, you know, for a really huge earthquake, we're seeing, you know, some signs of change, whether it's foreshocks or increased seismicity or tremor, or, you know, I don't think it's going to happen out of the blue just like that. So, okay.
Should we talk about any of these other scenarios of how the rift might get fed, just for science sake? Too much time.
If you want, you mean talking about this concept? I mean, I think we'll leave that out for now, perhaps, okay. for now. But maybe I can see if there's any questions right here that refer to this in particular. How thick is a water lens?
Well, it changes with elevation. It's called a lens because it mirrors the kind of lens shape of the shield volcano. So it'd be thicker in the center of the island under the summits, and it tapers out to the edges of the island because it doesn't go below sea level. So it's like a lens shape. And so let's see, if it's almost 2,000 feet below the summit, that means it's about 2,000-ish feet above sea level above the summit. That makes sense. So it's roughly 2,000-ish feet thick is the freshwater lens within Kīlauea. Ballpark.
All right. Another question, you know, when we have these blockages, can it get pushed through the system on a rift zone?
That is a question, and we're often answering the question online is if the material falling back down into the volcano is remelted. And in general, it's not remelted very easily. Some material might be remelted after a period of time, a lengthy period of time being in contact with fresh lava. It'll start to remelt. But most of the cold rock that collapsed down is probably going to stay rock. And then over time, as the volcano grows, it could be re-intruded and start to be a new magma chamber form in the space that was created by all the collapsing at the summit. But in general, all of the collapsed material is not remelting and it's not transiting through the volcano. And we don't really know, but there's lots of ways for different materials to be moving through the system. There's ways for pieces of rock and faults that are all right next to each other to slip and move and slide within there, and those may be causes for apparent blockages. That might be part of the reason the lava came out at Kīlauea rather than continuing down to the lower rift. There may have been some kind of slab of material that was jostled and was obstructing the flow to some degree, but it's really, really hard to infer any of that kind of internal structure from the surface.
I like that when you called them constrictions earlier.
Yeah, constriction is probably a better idea than blockage.
Because we don't know if it's actually something physical blockage. That's a possibility. It certainly could happen, but it could also be the shape of the crack. It could be the fact that it's got an easier path to the surface that's really open as well, right?
It all comes down to what pressure is available, right? Is there enough pressure to squeeze through the crack? Is there enough pressure to move a blockage?
Right.
And so there's all kinds of scenarios we might be able to imagine.
Right, and like we were talking earlier, if we have two cracks to choose from, and one is just like a rock that you got to break and make a new crack, and one's a crack that's already there with some magma in it, it's easier to kind of stick your fingers into that gooey magma crack and wedge, you know, you can actually push into that a little easier, right, and kind of wedge that thing open easier than you could the actual solid rock. So that's, you know, there's that kind of dynamic as well. You know, if you have enough let's say, blockage that you can't get through it, you can still just crack the rock. That's the size of the pressure we're talking about. And if you don't have quite the pressure to crack the rock, then maybe it doesn't take as much. You can still push through the rift system with slightly less than that, and possibly clear some kind of constriction, whatever happens to be there. So that was a good one. Here's another one. How can there be pockets of lava? Wouldn't they cool and harden inside the rift zone?
Wouldn't they cool and harden? They would, but again, just like it takes so long for the lava flow channel of Fissure 8 to cool, parts of it will be hot for years. Parts of it down near Kapoho will have magma, hot lava under the crust, 20, 40 feet down under the crust for years and decades even. If you drilled down there, you'd find a pocket of hot lava in there still. And when it's deep underground, we're talking thousands of feet underground in this diagram, the lava is so insulated, and especially if it's just sitting there and gas is not escaping from it, carrying away the heat, it stays like perfectly insulated for hundreds, even thousands, and sometimes even millions of years. The lava can stay hot underground. And so that's where we step off into those are parts of explanations for why some of the other islands have erupted recently. Old packets of lava are still hot down inside. And so we think probably all along the rift, there are areas where lava has been in storage or is maybe completely cut off, like we think might have been the case at Fissure 17's source. Might have been a completely isolated pocket of lava. It could have been as recently deposited there as 1924 or 1955. It also could have been hundreds of years before that. But it can stay hot underground for an amazing amount of time, especially if there's a lot of it, and it's not degassing. So.
Yeah, for sure. Yeah. So just one example to add to you guys is a famous example up in the park of Kīlauea. So what, kind of first of all, the shape of the lava body makes a difference to like how quickly it cools. The thinner it is, like the more like a dike it is, the probably quicker it cools, and the more like a magma chamber, the bigger, thicker, rounder areas, the slower it cools because it's less surface area. That's what matters. But in the case of Kīlauea, which was a crater that was filled by an eruption of about a month, ended up being 440 feet deep lava lake within the crater. Because that is the place where the scientists actually drilled through the cooling crust of the lava lake and saw how far down it was to reach the liquid. They actually have a whole cooling profile. And cut to the chase is it took 36 years for that whole lava lake to become solid. And the temperature at which it became solid was about 1,000 degrees Celsius. Right, so that means not that it got cold, because today still a thing is steaming up there, right? And it's been, 60 years. So it's still steaming that long later. That's how hot it still is. Hot enough to boil rainwater and turn it into steam and bring it out of the ground. That's how hot it can be still 60 years later. In that case, 440 feet thick. Nothing Kapoho is 440 feet thick. So, it's not likely to be that exact dynamic, but just an illustration for you guys of how long things can be hot underground. And that's why when we say, okay, well, these cracks might be steaming for months, months is really not, it's kind of a short end of it, right? Some of those fissures might be steaming for years, like the ones from 55, which were the steam vent in and all of that area down on the highway, So that's kind of how that all ties together. So you got to tell me what time we got. We're going to cut off questions or not. But
yeah, I'd like to do questions. I'll go soon.
Okay, so another question is, could there be lahars in the lower chamber if there's water in there?
Oh.
And let's define lahars first, yeah?
Vocabulary term. So a lahar is a volcanic mud flow. And so it's something that happens on the surface, and it's usually from volcanoes that have a lot of glacial ice and snow near their active areas or their summit, and those glaciers melt, mixed with ash sometimes, or mixed with sediment, and you get flowing concrete, which can flow incredibly fast. It's like a concrete flow almost in some cases. It doesn't set like concrete, it depends on the ash. But so the term lahar is referring to something that flows like water on the surface downhill, and it's a mixture of the meltwater from the volcanic eruption and glaciers and sediment or ash. And so Hawaiian volcanoes aren't really at risk for that because we don't have glaciers. We know there's evidence that Mauna Kea used to have glaciers on the summit, and it might have actually produced lahar mud flows while it was erupting beneath the glaciers.
Yeah, especially when you have the ash.
Yeah, the ash is a big component of it. And so the type of activity when water gets into the magma chamber would be called phreatic or phreatomagmatic steam explosions, and it doesn't involve a flow of mud. Even after it explodes to the surface because of the steam, it won't create a mud flow by that process.
Yeah, so yeah, good answer. Lahar is kind of a surface thing, and we could have interactions, but they're not going to be lahars down inside of the ground right there. And following up on that, if the lower chamber is cut off, is there a possibility it breaks out anywhere in a rift zone now? Or if it's cut off from the path?
Talk about it.
Okay, do it.
That's the question that took us. So
yeah,
you can see, these drawings are based on some of the best minds, and some of the best data have given us this drawing to start with.
It kind of collects information from probably at least a dozen different studies of like constraints and where things have to be.
And they drew their cartoon based on that information, and so that's why these funny shapes. This is legitimate science was done to make these funny shapes. And so you can see they think that the most likely connection to the East Rift is through this southern magma chamber, and so magma has to transit through there somehow. And the question is this connection lost to the East Rift over here, or is the collapsing affecting the upper parts of the South Chamber? And we can't be really certain at this moment, but I can draw for you. There's also sometimes postulated that maybe Mauna Ulu was getting deeper source magma from somewhere way over here. And then there's also this idea of the mysterious deep rift, which I'll draw down here like this in dotted red lines. So the deep rift zone is the idea that there could be magma down here deep below either of the rifts. And it could be pockets of magma, or it could be magma that's occasionally resupplied. And there's some people that argue that the deep rift could supply magma to the East Rift eruptions, or that there could be connections through the deep rift from the conduit bypassing the summit. And so all of these ideas are not in our original cartoon because they're seen as less likely.
Right.
And we don't have ways of determining that. It's something the geologists are always scanning. Would this fit an explanation for what we're seeing on the surface? And there's only shaky indication that there's even lava down in the East Rift. And there's only some suggestions that it might work with our model if the lava was coming from deeper. But in general, it's considered that all of the connections are coming from the shallow system and the deep summit reservoir, south summit reservoir.
So what I would say is that we don't need that. We don't need any of this,
Yeah.
any of this stuff. So it's kind of overcomplicating. There's no need for that, and we don't really see any huge body of evidence, I'll call it, because there is like little pieces of evidence that maybe point to that. One of those might be the chemistry of the rocks that came out of the ground at Mauna Ulu. You might say, well, the way that these rocks crystallized underground and must have been from a deeper source. But then you got to wonder, okay, is it coming, through a path like this? Or is it coming through a path like this? Or like, what's the path up? How is it a matter of how long it stays underground? So it's not so simple and straightforward, but it is an idea that's talked about, and we want to just kind of mention it for you guys, especially in how it relates to that, because that's kind of the Joker card, right? Like, we're playing by the rules here. If someone comes and throws a Joker into our game, then we don't know where we go from there. But playing by all the rules that we've laid out and been following this entire time with you guys, the whole last 3 months, we don't need any of that deep stuff.
Yep.
And I believe that we just have to deal with this problem of what's going on right in here as a real solution of what happens next.
Right.
So maybe let's take maybe 2 or 3 more, depending on how quick they are, because I can wrap it up. Did the lava from 55 just hang out in the rift zone until this eruption?
did the lava from 55 hang out in the rift zone? And this is a puzzle that I've heard geologists explain it in a couple different ways. So on the one hand, you can think of when our intrusions pushed past Pu'o'o and we had fresh lava was intruding deeper and deeper into the East Rift and under Leilani, there could have been 1955 lava sitting in that conduit that got squeezed out as the conduits were formed, as the fractures reached the surface forming our fissures. It was pushed out ahead of all the fresh stuff. In another model, which I tend to think of more, remember that these aren't like pipes. They're usually take the form of a vertical blade. They're narrow and tall, and there's lots of them. Probably all sides. Sorry?
Yeah, well, how thick did the USGS estimate this blade is that's feeding us?
This blade is only 5 meters across, so like that's only about 15 feet wide near the surface.
The one feeding this, that fed this eruption, that's eruption. What the models
That's all it is
suggest.
15 feet wide, squeezed in there and displaced the mountain. And so what I tend to envision happening in the East Rift, and this is one of the explanations for it, is that as one intrusion is moving through, it's tall and narrow following a fault line or a crack, and as it expands with lava, it's able to push out and it compresses the cracks that are on either side of it. Pushes out and compresses them. We have evidence that that kind of thing is happening. And so 1955 was either ahead in the same blade as it pushed forward, or it was sitting in there adjacent to it and it got elbowed out of the way as the new intrusion moved into it. And then, you know, we're talking about when the intrusion is moving in, it's breaking all the rocks to the surface. And so you could elbow the 1955 out of the way, it reaches the surface through the cracks, and then later the new intrusion uses those same cracks and comes out to the surface. So those are the two kind of models of how that happened, and I've heard it described both ways.
Yeah,
and
so it's likely that 55 lava got erupted during this event, and it's likely that the 55 lava still down there that did not get erupted is still going to sit down there for a while longer that did not get mobilized through here. So that's both of those things happening. Well, I see Anthony's joining us. Hi, Anthony. Thanks for joining us. We used your photographs earlier. Thank you for that. And let me see what other. Let's find one or two questions to end with here. Here's a quick one. How will a hurricane affect events? It will likely not affect events at all. So that's a quick one. And okay, we have a civil question. Will lava-covered areas and roads be cut off, removed, or is it just left? That's normally in Hawaii, we actually rebulldoze the roads that are covered in lava at some point, but it's not going to be anytime soon. They want to make sure that it's worth the money to do that. They're not going to get covered again immediately. So let me see. I think we've caught up here. So see Anthony saying he's got more photos. Awesome. So yeah, we'll promote that. I forgot to tag you initially, Anthony. I'll tag you here when we wrap this up here tonight. And
definitely, please, anyone in the air, more pictures within the vents. It is important. At least for me, I want to see what's happening in there. So wherever we get some images of if there's lava in that vent, it means something. So
yeah, so for sure. Anthony flew for Pu'o'o as well, so awesome. We'll check out Anthony's pictures soon. You know, you guys go check out Anthony's feed. The ones he posted earlier on Hawaii Tracker. I'm not sure if he's going to put those other ones up there as well, but either way you can find him through there. The hurricane is the last questions we're getting. Should we do a quick hurricane wrap-up here real quick, or you want to leave it at that?
Well, yeah, I mean, we should at least make the nod. The hurricane is the more concerning thing this week.
Okay, hold on. Here.
Sorry.
Let's make sure you can get heard.
Yeah, we need to be heard, so sometimes we have sound issues when we do the selfie mode, and the hurricane is the most concerning thing this week. We can talk about the volcano theory and what might happen next and wait for more signs, but the volcano is quiet right now, and we're not getting any indication of it waking up. Especially this week where we have a major storm that is going to at least graze us and has a chance of really affecting this island as well as basically all of the rest of the islands. So the hurricane is the ball to keep your eyes on and prepare accordingly for it. So it's not time to be complacent about the volcano ever, but this week definitely prioritize the hurricane is the thing we know is happening, and so we should react to that first. Yeah.
All right, so yeah, I'm just gonna show you guys, real quick, a couple graphics real quick. This is all from the NOAA website, Central Pacific Hurricane Center, and those won't go into too much detail, but here's the probably to me one of the two relevant plots. The earliest reasonable arrival time of tropical storm force winds, that's about 40 miles an hour. So they're saying that down here in the Puna region, the earliest arrival time is around Wednesday morning, and it's showing that at that point we have about a 10% chance of tropical storm force winds in Puna. It's a lot higher over here, maybe 30% by South Point and South Kona, right? And of course you guys can look that Maui is actually worse than Puna, as is Oahu as well. So those of you guys on other islands have to be concerned about this as well, right? It's past time to be preparing for this. So if you haven't yet, get on it, because that's the time is the clock is ticking for that. So that's the earliest arrival time, earliest reasonable, and they also have plotted what they think is the most likely arrival times. So rather than Wednesday morning, they actually say more reasonable, it's overnight Wednesday, between Wednesday and Thursday, impacting Puna area. And you can kind of see the probabilities don't really change a whole lot, right? Still a little bit lower over here on the other side of the Maunas, Mauna Kea, Mauna Kea over here. So the Puna area is a little bit protected slightly, and everything beyond that on the other side of the island and all the other islands are facing this threat head on, essentially, right there. So that's what we're dealing with right there, and we'll give you guys another update as well tomorrow. You guys keep abreast of that. I know that Hawaii Tracker has been putting out hurricane updates as often as possible. I believe that Harry Durgan and Ryan Finley have been leading those posts, and any of you guys who want to add to that or post more information can actually put those on there as comments as well, right? So I know that everyone should be getting prepared for this. This is definitely a huge threat for us. We all hope that it just kind of flies by and nothing happens, as most often happens to us. But if this is one of those that doesn't do that, we better be ready and not be like, oh crap, it's too late now, right? So that's why we're talking about this now, ahead of time, talking about it yesterday and the day before to some degree as well. But no, so this is definitely a serious situation. We hope to dodge it, but we're not anywhere near that time where we can relax about this. So there is that word on a hurricane.
Very good. Very good.
So I think we better wrap it up. We've been chatting for a while with you guys, and I'm sure it was worth it with all the illustrations and all that. We'll see, more questions we can get, and more illustrations. We have the board now to draw for you guys whenever needed. So we will talk to you guys again shortly. And in the meantime, for now, we will say aloha and
stay classy, Puna.